This is Pre Calc chapter 12.1, an introduction to limits. So this last part of the year, what we're going to do is we're going to try to get you ready for calculus. And one of the major topics in calculus is the idea of what a limit is. And before we get started in this chapter, I need to say that limits are getting into a different branch of mathematics. You have done everything that you could do in algebra. Algebra is finite. It starts in like the 4th, 5th, 6th grade where you start isolating and solving for variables, and it goes through right now. And then you've done everything algebraic. And that's why there's other branches of mathematics. There's calculus, trig, upper level branches of mathematics, and this is the precursor to some of that upper level stuff. Now there'll be a lot of algebra buried within this stuff, but we're going to start this first section, part 1, an introduction to limits, and we're going to start it with a review of special functions. So we have a couple of things here. We're going to do this from a graphical standpoint, so we're going to graph a bunch here today. Have your graphing calculators out, hit pause, go get them if you need to. Have another calculator open with Desmos if you want, or another device, and we'll go from there. So first of all, we have a piecewise function, and piecewise functions show up quite a bit in this stuff. And I have a picture and some different things. So first of all, f of x equals 7 for x is less than -2, x squared from -2 to 1, and x for x greater than or equal to 1. And first of all, what are these things called? Well, f of x equals 7 is called a constant function. X squared is our quadratic function. And x is our linear function. Sometimes because it's just x, it's also sometimes called the identity function. So we have some functions that we know what they are, and we kind of know the shape for them. So I'm gonna draw some pictures for these, and we'll see where we're at. So f of x equals 7. There are actually 3 chunks to this graph. Chunk 1 is f of x equals 7, and that's the same as saying it's constantly 7. 1, 2, 3, 4, 5, 6, 7. So if I was going to draw that in, I would draw in a line right there. That's a y equals 7 line, a lazy line at 7. 5, 6, 7. And what we do for a piecewise graph is we chunk it up into pieces. And this little chunk right here gives me the piece. We want to have the graph equal to 7 for everywhere where x is less than -2. So here's -2. I go up to the graph, and I want all that, that should be open circle because it's less than, and I want everything less than -2 tells me to go everything this way. So that chunk is right there. Now I'm going to do x squared. X squared, we know what that looks like. And then it'd be over 2 up 4, and over 2 up 4, and I have this. And I start by dotting them in, and then I'll go back and after I dot them in, I'll go back and I'll make solid what I need to. Sorry about those little extra chunks there. But this wants to go from -2 and inclusive, look, it's or equal to. So from -2 here, including that one, all the way to 1. And at 1, it's not or equal to, so I want an open dot. So for this graph, it wants to go from there to there in an x value. That's the chunk, that's the piece that I'm going to grab. So it's this much right here. And then the last one is x, and that's for x equals 1. So that right there, that's 1 over 1 x plus 1. It's the identity line. It's this one right here. Okay, and then it comes down here also. And then for that line, I want all values x greater than or equal to 1. So here's 1, and that line does go through that same spot as a parabola. So I'm going to have an open circle and a closed circle, and then it wants everything greater than 1. So I go like that. And that's called a piecewise graph. I take a piece, that piece, I take that piece, and I take that piece, and I put them all together into one graph, which is why they call it a piecewise graph. But this graph really, is it continuous or non-continuous? Well, it's definitely not continuous here on the y-axis, but it is continuous along the x-axis because it goes here. I have an open circle and a closed circle right below it, and then it continues, and then it goes like this. And what we're going to find in limits is that these spots where this happens, where there's a break in the graph, things are going to happen. We're going to have spots here that have limits and some that don't have limits, and we'll have to talk about that. But the first overriding concept here is that's what a piecewise graph is. Okay, so a graph with point discontinuity. Now, I don't completely expect you to know what this graph looks like. In fact, I'd be shocked if you did. But you should be able to put it on your graphing calculator. So I'm going to do that now. What I want you to do is either grab Desmos or grab your graphing calculator, and let's look at that. So I'm gonna use my fraction key, alpha f1, and I'm gonna plug in the top as x to the third minus x squared plus x minus 1. And on the bottom, I'm going to plug in x minus 1. And I'm going to graph it. Mine is still thinking. And I got a parabola is what I got. Okay. And that is kind of interesting that I have an x cubed and it's a parabola. X cubed, I would kind of think it would be something like this, but oh wait, I have an x cubed on top and a 1x on the bottom. I bet that 1x cubed there, and I bet they kind of wipe each other out, so I get this parabola looking thing. And I'm going to draw that parabola in right here. I'm going to go like that, and I'm just going to kind of draw it right in there. But there's something going on here that that we need to talk about, we need to discuss. And really, a rational graph like this, whenever you have an x on the bottom, you have a value that cannot happen. It's called a point discontinuity for this. We would also describe it as a domain restriction. So I know I can't have 0 on the bottom of the fraction. So if I said x minus 1 equal to 0, I will get an x value that is 1. And what I just found out there is anytime I put 1 in here, I will get the graph to blow up. I will get something that doesn't show up. But I notice right here at 1, if I go over 1 on my graph and I go up, the graph is continuous. Well, that's because my graph doesn't have enough pixelation, enough pixels. It's not high enough resolution. But if you took your cursor, and I know I always have people in class try this. If you take your cursor and you put it right on top, if you zoom in enough times on that spot, and I mean a lot of times, I mean you have to zoom like 10 or 11 times, or if you take Desmos and you squeeze it, it'll start getting funky at this point, to the point where there's like a little hole here. And here, let's have some fun with this. We gotta have some fun. I gotta find. Oh, here, this will work. So it's kind of like this. There's a little hole there. So it's kind of like doo doo doo. It's okay. I'm big enough. We're good. He was right over the top of it. But that hole is really kind of skinny. So it's like, doo-dee-doo. It's a queen. Doo-dee-doo. 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 Oh, no! Whoosh. Where if you had something thin enough, theoretically, it would fall right through that hole. And you have this little point here, and we label that point with an open circle. It's called point discontinuity. And that's also going to show up as we go through this. So a couple of algebra concepts that we're going to do. Okay, so limits, thing 1. What is a limit? A limit is a value of a function as the function f of x becomes arbitrarily close to a unique number L as the function approaches c from either side. First of all, arbitrarily close. It's like this. Like so close that you can't even see the distance between them anymore. Like arbitrarily close is like as close as you could possibly think. I mean, I'm talking like if you're in science class, like Planck distance close, like infinity in reverse close, like as close as you could possibly get those two values to hit each other. So that's what a limit is. Like what happens, like I have this pot in space, like, and then I got this graph that comes into it and it gets close here, and this graph that comes and gets close to here. And as those two values, as they approach each other, what we're asking ourselves is what y value occurs as I approach left and right sides of some specific point. And what we're going to start off with this, and this is the notation, the limit as f of x, the limit of f of x as x approaches c is equal to some value L, just some, that'll be your answer over here. And that's really what we're looking for, is we're looking what happens on both sides of the graph. So we'll take the graph and we'll look at it and we'll see what happens when those two values get really, really close to each other. So we can do this with a table, we can do this with a graph. There are a lot of ways to do this, but one way we like to do this is with a table. And you are going to need, you're going to need some type of grapher that will allow you to get to a table. I think Desmos has a table on it if you're using Desmos. I'm not real sure on the setup. I'm going to show you how to use this. This is probably the way you're going to want to go. Okay? So first of all, I'm going to type in, and I'm typing into y equals, so we'll clear off what we got here. So I got a blank screen. I'm on that screen, y equals, and I'm going to type in 3x minus 2. 3x minus 2. And now what I want to do is I want to set up my table. And I want to set up my table so I see values really, really close to the value in question. And the value in question is 2. So what we're asking ourselves is, if I graph this thing, what happens really close to 2? What happens on both sides of 2, for lack of a better way of describing it? So I'm going to go to second, and there's a little table set button. It's right there in blue. I hit second, table set, and it takes me to this spot. It takes me to a lot of different things. It says table setup, table start. Well, I'm going to start my table at 2. And then the next thing is delta table. And delta table means if I change my table, what do I want it to change by? And what I would like to do is I would like to see what happens on each side of 2, like barely. So I want to change my delta value. I'm going to change it by a really small number. So I'm going to change by 0.001. So my values that I have there, I have a delta table of 2. So I'm starting at 2 and I'm changing it by 0.001. And your table key is right up here in the upper right. So I'm going to go second table now. And it's going to tell me values. And what I do is I kind of cursor down so I can see. I see 2 there is the one without the decimal. And then I see a number on each side of 2. What I'm asking myself is, on each side of 2, what is the value? So from a graphical perspective, 3x minus 2, 1, 2. Then it's up 1, 2, 3 over 1. So from a graphical perspective, the graph looks something like this. And we're asking ourselves, here I am at 2. What happens as I get closer and closer to 2? And the table's telling me on each side of 2, one of the values there is 3.997, and the other value is 4.003. And I notice 3.997 and 4.003, those two numbers are really close to 4. So your value here, your limit, is 4. Now the question, why not just go to the number 2, look at the 4, and write down the 4? Well, that's a valid question, and we'll hope to answer that as we go through this discussion on limits. That is something that you can do. So let's try the next one. And like I said, this is the precursor to something that's really big. So hopefully you'll have questions as we go along. You won't understand everything completely, but hopefully we'll clean it up as we go through it. So I'm going to go back to y equals. I'm going to clear that off. I'm going to enter that in y1 on my graphing calculator. So, let me see here. Y equals, I need to hit my alpha F1 to get my fraction key again. So on top, I'm going to input x. On the bottom, I'm going to go square root of x plus 1. Cursor over, and I'll put minus 1. So looks like that. Okay, and I'm going to hit enter. I have everything where I need it. And now I want to set up my table again. Well, I don't want my table to start at 2 this time. I want my table to start at 0 because I want to figure out what happens around 0. So I'm going to go back to my table set. again, it is second function key, and there's a little table set right there, the little second one over. It's in blue, table set right there. And I'm going to start my table at 0 this time, and I still want it to change by a really small increment. I still want it to change by 0.001. And I'm going to hit my table, and I'm going to see what this looks like. And I notice, as I cursor up, I notice at 0, this time it says error. Well, this time I couldn't go right to 0 and figure out what it is. Because at 0, it has nothing. But that does not mean that there is no limit. So I got this table value, and I see on one side of 0, I see at negative 0.001 is 1.995. I'm just going to write these values down. Negative 0.001, my value is 1.9995. And at 0.001, the value is 2.0005. And I notice those two numbers, they're getting closer and closer to each other. If I look up in the list and then I look down in the list, I notice as the numbers converge on 2, or as the numbers converge on 0, I get a value of 2. So my limit is 2. Even though at 0, there's nothing. I get 2 at really close to 0. I care what happens on each side of 0. And by the way, if I hit the graph button, it's a funky looking graph. And that one right there actually, see if you can see it. That one right there actually has a point discontinuity at 0. If you zoomed in on 0, if you zoomed in, let's see, this one looks like this. If you zoomed in right there, there'd be a hole there. And you could maybe even do that on Desmos or zoom in on your graphing calculator. You could go in and you could find that hole. And the last one, we'll get 2 more. All right, let's go to y equals. Let's clear off what we got. And I'm going to type in the absolute value. If you hit the math folder and go under, let me see, where is absolute value? Oh, go under, in the math folder under NUM, there's one called ABS. And mine actually gives me my absolute value bars. Maybe you can see that. X, and then I put divided by X, and I didn't use a fraction bar, I just hit X divided by X. And let's graph that thing. Oh, so I got a picture of it right there. My picture is 2 lines coming in from each side. It looks like that. But I'm going to go to my table. I think I still got my table set up okay from the last one. And my table says at negative 0.001, I get a value of negative 1. And at 0.001, I get a value of positive 1. And those two values, those table values, they're not approaching each other. Okay? I do a little demo here. Oftentimes in class when I say, okay, here's what we're actually trying to get. We're trying to get this value over here, and here's the graph over here. It's going like, and then the value over here. So you got these two graphs, and they're kind of, and maybe they're going up and down, and they're going around. And in the end, as they converge on that number, we're trying to get that to happen. And when we don't get that to happen, if we get something like this, or this, or this, where these two numbers don't come in and converge on each other, then we say the limit does not exist. It's straight up. I mean, Mean Girls is a popular movie. There was a scene in Mean Girls where she was at a math competition and she looks at the board and she's, oh, the limit does not exist. We're straight up in that section. We're in, oh, the limit does not exist. So here we are, and we have this number, and just from a graphical perspective, I mean, one of them was coming in like this, and one of them was coming in like this, and we're trying to get closer and closer to 0, and at 0, we don't get this value where those two numbers, where they converge. So what we have here, if the numbers don't come closer to each other, we actually say the limit does not exist. The limit does not exist, and we'll put DNE for does not exist. All right, and the last one. We'll plug that one in our graphing calculators. Y equals 1. I'm going to go ahead and use a fraction button. 1 divided by x squared. And I still want the limit at 0. So I could go to my table set, but my table is still set up where it has 0 and then it changes by 0.001. So I'm still okay. So I'm going to go back to my table. And I get, wow, I get really, really big numbers. I got, like, one of them was scientific notation. Look at that. At 0, it says error. Oh, I can't plug 0 in on the bottom of the fraction. But at negative 0.001 and at 0.001, we're looking at those values that happen. I got 1e6, which is 1 million. And I got a million here. Those are really big numbers. I'm going to hit the graph button. I want to see what's going on. Okay. Ooh, I got that. So what we're looking at is we're looking at to see what happens when this graph converges around 0. So you have these two ends of the graph, and they're getting closer to each other, and they're coming in, and all of a sudden they start going like this, and they start, they start going up. And I'm going to tell you, it really depends on the book manufacturer that you're in. Some will say, what's the limit? The limit does not exist because they don't approach each other. The limit does not exist. I have seen some books say, yeah, but they're going at the same rate, and they have to go at the same rate for this to happen. If one goes like this really fast and the other one can't catch it, I mean, if they're going at the same rate and approaching the same value and going up, I have seen some books say the limit is infinity because it's going up. The limit is infinity. I think the standard way, the standard method is to say if it doesn't approach a number, we have a limit that does not exist. So I'm going to go with that one. But if you see this idea of they're approaching the same, they're approaching it from both sides, they're going up at the same rate, and you want to say the limit approaches infinity, that might occur. So you might notice that in problem 1, the limit as x approaches 2 is exactly the same as the value of directly substituting 2 into the equation. In 2, 3, and 4, if I try to plug a 0 straight in, it blows up. If I plug, this one said error. If I plug a 0 in there, I have the square root of 1, which is 1 minus 1 is 0. I get 0 on the bottom of the fraction. I can't do it. If I plug a 0 in here, I get 0 on the bottom of the fraction. It blows up. I can't do it. And if I plug a 0 in here, I get 0 on the bottom of the fraction, and I can't do it. That does not mean the limit does not exist. This one I could directly substitute in and get a 4. This one I could directly substitute it in. It didn't work, so I went to a graph, and I got 2. These other two, they had limits that did not exist, but it wasn't because when I plugged the number in, it didn't work. It was because at the number, I did not get this value where these two numbers converged at around this other number. So if we can directly substitute, we like, but we won't. There are many ways to evaluate a limit using features on your graphing calculators, including a table of values, the trace feature, zooming. We will do all of these. We are going to use our graphing calculators. We are going to use the tables. We'll look at the tables to help us come up with the answers and go from there. So some conditions of limits. Number 1, the existence or non-existence of f of x at x equals c has no bearing on the existence of a limit. Well, that's Greek. The existence or non-existence of the so even if the graph exists or doesn't exist at the specific number, it doesn't necessarily mean there won't be a limit. That was like example right here. This graph right here had a hole at 0. There was a hole there. But we still got a limit because on each side of the hole, we were getting closer and closer to 2. Okay? That's number 1. And this says like, this is example number 2. A limit, number 2. A limit does not exist if f of x approaches different values from the left and the right of c. That was like example number 3. You had one graph coming in this way and one graph coming in this way, and they did not converge on anything. So this was like example number 3 was like that. And number 3, if the function f of x increases without bound at c, the function has no limit. And that was like these two numbers coming in, and they take off like that. And this was like example number 4 was like that. Or sometimes some books will say the limit is infinity. Clear as mud, I know. It's okay. This will be a process. Get through this limit, and we'll get these down. These are kind of fun. It's a different branch of thinking, a different style of thinking about really about graphs and numbers. All right. The last thing I want to do today is I want to graph you. I want to graph some pictures of this, show you what it's going to look like on a graph, some of these conditions. So number 1, the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit. Let's put right there, we're going to go out to 3, and I'm going to go up to 4, and I'm going to put a hole. And I'm completely making this graph up. I'm doing this, and I'm just wiggling them around, and then eventually they're going to come together in that hole. So maybe this graph does some random, it doesn't matter, goes to there, and then out the back side it kind of goes like that. And I 100% made that graph up. Okay? But there's a hole in the graph. Somehow, some way, this graph has a hole right here. That does not mean that there's not a limit. It just means at that value, you get nothing. And it's this easy. So I'm going to go over to 3. So let's find the limit of this graph, the limit as x approaches 3. Now what that means is from the left side and from the right side of 3, I want these two values to come together. And it's almost like, I don't know, it's almost like you're trying to pop a pimple or something. Like here it comes in, and I try to get, and if those two things come together, if that happens, then we have a limit. So I notice from this side and I notice from this side, it's converging. And so what is the value? And from this graph, I can just look at it. At 3, those two graphs are converging at 4 from the left and the right. Limit as x approaches 3 is 4. And we have it. There's a hole in the graph. It can still have a limit. Number 2. A limit does not exist if f of x approaches different values from the left and the right side of C. So we could have a graph that jumps. And again, completely made up here. So let's go to 2 this time. And this graph comes in like this, and it comes, and then, oh, there's an open circle, and then it jumps up here. Maybe it's a piecewise graph, and it jumps up here, and then at 3, I put a solid dot, and it goes up forever. And that jump, here I got this graph coming in like this, and then I got this graph up here, and when I converge around this point of 2, I'm finding the limit. I just made this up. The limit as x goes to 2. Well, on the left and on the right side of 2, I don't get anything, so I get the limit does not exist. And I should denote here that just because the limit doesn't exist at 2 does not mean that the limit won't exist somewhere else. In fact, the only place that this one has a limit that does not exist is at 2. If I went to 1, 2, 3, I would have this value, this limit value. Maybe it's 1, 2. So if I found the limit as x approaches -3 here, as I get closer and closer to -3, I do have this value. And that value right there, what value am I approaching on both sides? That value would be -2. The value being -2 there. So I have a limit on the graph here. In fact, I have a limit everywhere except that spot where they don't come together. Okay, or the graph goes to opposite infinity. So there's a lot of times where you'll have a graph that comes like this. We actually graphed this a long time ago. It's called laces. And there's a spot on this graph where I do not get them to come together. So what we say is at that spot the limit does not exist. Everywhere else the limit would exist. So I would say this value right here, I would find the limit as x approaches 0. As I come closer and closer to 0 from the left and the right, I would say the limit does not exist. Again, here, if I went 1, 2, 3, 4, if I went here, the limit would exist there. In fact, the limit would exist everywhere else except at that spot where you don't get the convergence when you get it to go like this. And there's actually a weird one that oscillates, and I don't do this one a whole lot, but there's a graph that from one side it goes oscillates sides of the x-axis, and it actually goes like this. And then there's another one, it comes out the back side. And if it oscillates weird like that, if you ever get this weird one right there, the limit as x approaches 0, as I get closer and closer to 0, that one does not exist. We don't actually run into the oscillation one. Maybe one or two problems, you'll see what that looks like. And the last one. If the function increases without bound at c, the function has no limit at that value c. So let's go negative this time. And let's go like this. And then I'm going to come down like this. So I have this value of c, the c value where they're coming in from both sides and they're going up like that. And that value is right here. Okay, and we would say the limit as x approaches -3 on both sides, well, the limit does not exist. Okay, that would be a DNE, and we could do it, or we could say the limit, some books, maybe I'll see the limit, I'll say the limit is infinity because they're going up at the same rate. I think DNE is standard though. We could do the same thing in a down format. Maybe it comes like this, and it goes like this. Something like that. Do you know where the limit doesn't exist on that? You would say the limit as x goes to 4 does not exist. All right, that's the end of part 1. That's a lot of theory. Man, a lot of theory. This is limit theory, and I like to look at it from a table of value standpoint and from a graphical standpoint. You're looking for convergence around a number, not necessarily what happens at that specific number. And that really makes it hard. And I understand that. But we're going to get through this. This is going to be awesome. I'm excited to talk about limits. I'm excited to get ready for calculus. And we're going to knock this out of the park. Have a great day.